Hello, this is Mr. Win, and this video is about analyzing graphs of polynomials and also finding their inverses. So the usual polynomials we'll see in this class will be of degree 1, 2, 3, 4, and 5. So y'all know 1 is linear, 2 is quadratic, 3 is cubic, 4 is quartic, and 5 is quintic. We've been doing a lot of quadratics, so now it's time to go up 1 degree to cubics, then up again to quartics, then up again to quintics. If you're curious about how a function looks, you can still sketch it according to AHK if it's given vertex form, but you must know the shape. For example, a quadratic is a U shape, a cubic is like a sideways S. You could type it in the calculator into y equals to see the graph if you have a calculator available, or worst case scenario, you can find multiple points and plot them yourself and try to connect it the best you can. This third option does involve picking lots of x's, plugging them all in to find their y's, and those x, y's pairs together are their coordinates. There's also patterns and trends you'll start to realize once you're working with enough of them. Next slide will have one of each type of graph for us to analyze. And keep this in mind when you see the graphs. What makes a function linear, quadratic, cubic, etc. is its degree, the highest exponent. But by just knowing the degree, you can figure out a lot of things. So here's 5 graphs. Here's a line, a U, a cubic, quartic, a quintic. And I have degrees of each and all these characters underneath the graph. But do you notice that the number of roots always match the degree? I told you the exponents of the number of answers are. So y'all know quadratics have 2 answers. There's 2 x-intercepts here. For linear, there's 1 x-intercept. For cubic, third power, there's 3 x-intercepts. For quartic, fourth power, there's 4 x-intercepts. 1, 2, 3, 4. And for a quintic, there are 5. 1, 2, 3, 4, 5. Alright, what else? Did you notice that there's always 1 less total minimum max than the degree? Linear's degree is 1, there's 0 minimums, there's 0 maximums. Quadratic, degree is 2, you subtract 1 from that. There's 1 max or min, depending if the u's flipped or not. For a cubic, there are 2 max and min together. Here's 1 maximum, here's 1 minimum. Alright, for quartic, degree 4, you subtract from 3, there's 3 max and mins together. So there's 2 minimums in this case, and 1 maximum. For quintic, degree is 5, subtract 1 is 4. So there's 4 mins and maxes. There's 2 maxes and 2 minimums for 4 total. And here's the one for the quadratic. Alright, did you notice that all degree polynomials always have one side going down and one side going up? So for linear, the left side, y is going to negative infinity. The right side, y is going to positive infinity. Cubic's also odd. For the left side, y is going down to negative infinity. Right side, y is going up to positive infinity. For quintic, odd exponent degree. Left side is going down to infinity, negative infinity. Right side is going up, positive infinity. Alright, so odd degrees always we call it end behavior, goes different directions. One's down, one's up. If it's even, for example, quadratic, the left side goes up to positive infinity, the right side goes up to positive infinity. Same for quartic. Left side goes up positive infinity, right side goes up positive infinity. This is how even degree polynomials work. Alright, we have fixed a little vocabulary, but that's okay. So when we had a quadratic, it was just a single minimum or maximum. But since we have higher degrees now, we don't have simple mins and maxes anymore. What we have are called relative mins and maximums. For this picture over here, here's a max. It's the top of a U shape, upside down U, but that's not the true max because this graph keeps going up forever. That's not the real highest point. It's only a maximum in its general location, so it's relative location. So now we're going to have a lot of relative minimums and maximums. There's still going to be a true absolute minimum maximum sometimes, but just keep in mind that they're mostly relative now. Those minimums and maximums combined to a single word are called extrema. Alright, so that's the total number of mins and maxes. Those points are also called turn points. It's because they're turning when you hit a maximum or minimum. For example, I'm going down, decreasing. Once I hit this minimum, I start going up. I'm decreasing. I turned around. So I went from down to up. As I go up to this maximum, I'm going to turn around and start going down. So those are what turn points do. Alright, anything else? That should be it. I would copy this down. The degree of the polynomial tells you a lot of information. The number of answers, the roots. Now this is real and imaginary, and that's always matching the degree. And remember, imaginary roots always come in plus minus pairs when we do the quadratic formula. The I stuff. Alright, also in my extrema, the mins and maxes, also turn points, is always the degree minus 1. And the end behavior, for even degrees, they go the same direction. For odd degrees, they go the opposite directions. One's up, one's down. Depends if the picture's flipped or not. All right, so we need to be able to analyze the graph by counting the key information. So for this graph, what's the smallest possible degree? Set the number extrema, minimums, maximum, turn points, real roots, imaginary roots, total roots. All right, so here's the picture. It's just counting. Count the easy things. My favorite to start with was the maximums. So here's the max, here's the max, here's the max. There's 3 maximums, and they're all relative because this arrow keeps going up forever. There's 3 maximums. I count minimums next. Here's the minimum. Well, here's the minimum. Here's the minimum. It's also 3. So if there's 3 mins and 3 maxes, that means there are 6 extrema, because those are mins and maxes. Also, another word for extrema is turn points. We turned around 6 times. Okay, remember the number of mins and maxes or extrema is always 1 less than the degree. So there's 6 turn points or 6 extrema. The degree should be 7. 7's odd. Is this graph going different directions? Yes, the left side's going down, the right side's going up. All right, if we know the degree, you know what my answers are. If the degree is 7, there's 7 answers. All right, let's count my, oops, not there. 7 total roots. All right. Then we're going to try to figure out how many of them are real. You just go to the graph, how many x-intercepts you actually see. Here's the x-intercept, here's the x-intercept, there's 3. There's 3 real roots. Now there's supposed to be 7 answers, so if there's only 3 real, 7 minus 3 means there's 4 imaginary. Alright, so that's the order I do. So just count the mins and maxes for the graph. That tells you the extrema, the turn points, and the degree. The degree then tells you how many answers there are. Then you can count how many x-intercepts you see and subtract that from the total answers for your imaginary. Alright, 2 more slides. Don't forget about the 0 location principle. Remember, that's the idea is if you have points but not the exact x-intercept, you can kind of figure out where the x-intercept is because 0 separates positive and negative numbers, or reverse that too. 0 separates negative and positive numbers. So remember, the idea is the y sign change. Find where the y value changes from positive to negative, or vice versa, from negative to positive. So it says the following table has points from the graph of f of x equals x cubed minus 4x squared plus 3x plus 1. So it's cubic, degree is 3, there could be up to 3 answers. It says find the approximate location of the roots. So you look at the y values, not the x's, but you use x as the location. So from negative 29 to negative 7, did it change signs? No, it's negative 10, negative. But from negative 7 to positive 1, yes, there's a sign change. All right. From negative to positive. All right, so we can say there's an answer. We'll say there's a root between x equals negative 1 and x equals 0. I use the x's for the location. All right, we keep looking. Positive 1, nope. Positive 1, negative 1, yes. Here's another sign change. Alright, so I usually don't write sign change, but I was right here. Root between x equals 1 and x equals 2. I look negative and positive. Oh, there's another one right there. It changed again. So there's going to be a root between x equals 2 and x equals 3. I keep looking, positive 1 to positive 13, positive, no change. All right, this table works for any kind of graph. Could be quintic, quartic, degree 10 if they wanted. I did have a graph of this just for y'all to see. And if you notice, there are 3 x-intercepts. One right here between negative 1 and 0, which is our first one. Here's one right here, that's between 2 and 3. Did I have it right? Oh, how does the scaling work? Here's another one. It's between, if their scaling is right, 2 to 3. Yeah, between 1 and 2 and then 2 and 3. Good. Now, we don't know what this exact x-coordinate of this thing is. We don't know the exact x-coordinate of this, right? It might be 1.5. Then this one might be like 2.9. We don't know. That's why we say it's between 2 and 3 for sure. All right. And the last one, inverses. So y'all know inverses. Change f of x to y, switch x and y, and solve for the new y. But now we're going to have exponents, but to get an exponent, you just use the correct root. So for number 1, just find the inverse of x, f of x, if f of x equals x cubed plus 8. So I make this y equals I'm going to switch x and y. So x equals y to third power plus 8. Then solve for y. I'm going to subtract 8. So x minus 8 equals y to third power. Now to get y is almost by itself. To get rid of third power, you have to do a third root. So instead of doing a square root, you can do a third root by putting a little 3 right here. And that cancels out. So the final answer is the cubed root of x minus 8 equals y, but instead of y, we call it f inverse x. Done. All right, the next one is kind of reverse. So this is find the inverse g of inverse x if g of x equals the fourth root of x minus 5. So same thing, make a y equals fourth root of x minus 5. Switch x and y. So x equals fourth root of y minus 5 and solve for y. Y is inside that fourth root sign, so we get rid of that root sign first. Remember, roots and powers cancel that out. So to get rid of that, I'm going to do fourth power both sides. Just like to get rid of square, you do a square power. To get rid of fourth, you do fourth power. So left side is now x to the fourth power equals the right side, the fourth root, fourth power cancels out, which is y minus 5. The last step, I'm going to add 5 to both sides. So my final answer is, I'll go over here, x to the fourth plus 5 equals y. But instead of y, we'll call it g inverse of x. All right, and then the most complicated one, find m inverse x if m of x equals that. So always y equals switch x and y. So x equals. Then solve for y. Now, y is part of the parentheses of the cube power. I forget it by itself. I gotta move the 2 and the 4 first. I'm gonna move the 4 over by adding it. So x plus 4 equals 2y plus 3 cubed. I gotta get rid of the 2 next by dividing by it. So it's x plus 4 all over 2 equals y plus 3 cubed. From there, I gotta get rid of the parentheses exponent. So I'm going to cube root both sides to get rid of that cube power. So we're going to have cube root of this giant fraction side, and that's okay. X plus 4 all over 2 equals y plus 3. Last thing is I'm going to subtract that 3. So the cube root of x plus 4 all over 2, this minus 3 is outside of it, equals y, but instead of y, we call it m inverse of x. So that's the steps of doing it. There's one more thing you have to keep in mind. You need to remember that inverses are the same picture reflected across the diagonal line y equals x. They're mirror images of each other. So the degree or highest exponent is odd, you're done. Nothing to change. But if it's even, you have to add domain restrictions. So remember, like a square root and a quadratic are inverses of each other, but the square root, half of u is not a full u. So if you start half of u, you got to end with half of u, or you start with a full u, you got to end with a full u. So if you had a full u, and you end up with a square root, you'd have to have a positive square and a negative square to combine to make the full sideways u. So same idea here. So my m inverse of x, this was third power, so I'm done. Third root. This f inverse, this third power, third root, I'm done here. The only one I have to fix is this g inverse x. This is the fourth. So because it's positive, I'm going to say we need the positive half. We'll say for, or if, or when g inverse of x is greater than, or sorry, not just x itself. Oops. So for, instead of when, x positive goes to positive. Now there's one more thing I forgot to say, and that's this. If there's a translation h, you have to use it. So since this is right 5, this 0 goes right 5 to 5. So only this one has a domain restriction, and usually won't have as many problems, but just mentioning it now. And that's it. Hope you enjoyed the video. Make sure you're asking questions in class. See you soon. Thanks again. Bye.